Thank you, Simon. And good morning, everyone. Before I start, a big thank you both to Simon and to Tim. I know how much work it is to put on such a great program, and I know everyone here appreciates that. And it's good to see so many faces here, some old and some new. As well as being a pleasure and an honour to start the conference, it's also a big responsibility. The working group, the OpenCL working group, has been working hard over the last 12 months, so I want to represent their efforts well. And of course, the OpenCL working group takes its responsibility to the large industry very seriously too. So we really want to use, as always, this IWOCL. This is our yearly get-together where we can not just talk to you, but also listen and find out what it is you need and what you think should happen with OpenCL to meet your needs. We have this kind of update presentation right now, and we also have the session that Simon mentioned earlier. So don't be shy. Tell us what you think and what you need. So let's start. So this, Tim gave you the title, State of the Nation. So what is State of the Nation? Well, OpenCL is alive and well and growing. If it didn't exist already, we'd have to invent it, because it's providing a solution to a unique need in the industry to deploy parallel software across diverse, heterogeneous processors. As the graphs from Simon's presentation showed, we're in kind of a steady state right now. I think there are more applications using OpenCL every day. There's interest not just in OpenCL, but also the related tools around SPIR, SPIR-V, and SYCL. At NVIDIA, we find more people are using our OpenCL implementation every year. And the working group has been working hard since the last IWOCL. That last IWOCL, if you remember, we released OpenCL 2.2. Since then, we've been doing a couple of things. We've been figuring out the roadmap and where we want to take OpenCL, but we've also been putting quite a lot of effort into a maintenance release for 2.2. It's normal, of course, to have maintenance releases for specifications. You find bugs to fix, clarifications, making the spec easier and clearer to use. And some of you might have spotted the social media yesterday. We have just put out a maintenance release for 2.2 here at IWOCL. But of course, life is never perfect. There's always things to consider and to address. And some of the things that the working group has been considering as we've been plotting a path forward is, what are the things that are not going as well as we would want? And some of the interesting observations are, we're still not getting a big uptick in the adoption of 2.x, 2.0, 1 and 2. OpenCL 1.2 remains the baseline, I would say widely deployed version of OpenCL. So we've been trying to understand why and what we can do to push things forward, and we'll talk about that during this presentation. Also, there is some deployment, I call it deployment friction in the industry. There are some key platforms, particularly some of the mobile platforms like Android, that don't have an officially supported OpenCL. Many GPU vendors do ship OpenCL on their particular GPUs, but it's not supported officially by Android, which makes things confusing for the developers. Now, not everyone, of course, is interested in mobile, but for those that want to have the dream of OpenCL portability come true, including mobile devices, this is kind of a big friction point in the industry. And we're finding that it's the embedded space that is perhaps the largest potential use, untapped potential use of OpenCL, an increasing amount of processing power for vision processing, inferencing, being put into small, low-power, low-cost devices with a real need for a real programming environment. But OpenCL right now is is locking out a lot of those smaller processors. We insist, for example, that they need 32-bit floating point. And most of those processors and those kinds of applications simply don't need that. And so we have this mismatch that we'd like to address. So looking forward, I think kind of the headline takeaway for what the working group thinks we should be doing going forward is deployment flexibility. We want to have more flexibility for implementers of OpenCL to deploy conformant implementations across an even wider range of processor types as the industry begins to embrace more architectures. And that includes delivery of OpenCL in safety-critical systems, self-driving cars kind of being the poster child for where safety matters. We really need to make sure that OpenCL is keeping up with the need for safety-critical certifications. But also, it's not just implementations. We want to have more deployment flexibility for applications. And that might sound weird, but we'll talk about this too. We want to enable OpenCL code to be deployed on other runtimes, not necessarily just the OpenCL runtime. So if you're a developer and you're investing in OpenCL, you can take that investment and deploy it in the places that you need. And we've been trying to figure out how to make that happen the best way. So that's kind of the summary. Let's start at the beginning now. So a brief summary of where we think we are. This is the OpenCL Evolution. It was interesting putting together this first handful of slides kind of summarizing the current status. Not a lot has changed since last year. It's kind of that Simon's graph, things are looking good but kind of flat. That's kind of the story of where we are with the current OpenCL. So these are the major releases since 1.2. About every 2 years we come up with a new version of the spec. Last IWOCL was 2.2, and I mentioned the maintenance release here that's just been released. So what did we put into the maintenance release? Well, first of all, don't panic. It's fully backwards compatible. We haven't broken anything. It's mainly clarifications and fixes to make sure that the implementations are all being consistent with each other. We're not expecting any application code changes to be necessary. But hopefully, if you're digging down into some of these details, you will find clear explanations and more consistency amongst the various implementations in the market. And if you remember last year, we also opened up the specification itself into open source, and we did get people putting issues into the GitHub repository, and we have fixed a bunch of those bugs that were reported. So thank you to everyone who took the time to file those bugs. They are being listened to and they are being fixed. Last year we put actually almost all of the specifications into open source. We didn't put the OpenCL language spec into open source because we were mainly focused on C++, but now we've filled in that gap. So now all the specs are in open source on the GitHub repository. We're using a consistent tool chain, which should make the specs consistent and hopefully easier to navigate. But probably more importantly for developers, this OpenCL SPIR v environment spec. The environment spec is the spec that defines which parts of SPIR v OpenCL uses. We've improved that spec, so if you're writing compiler front ends, it should be a lot easier for you to figure out what's valid SPIR v for OpenCL. And last but not least, we've unified headers. So now you can use one set headers for all the different versions of OpenCL and all of the extensions. So nothing too glamorous, but important as we continue to make OpenCL a more reliable platform. And if you weren't here last year or you blanked it out, the way we are open sourcing the specifications is quite straightforward. Now we're using ASCII Doctor. We have the ASCII Doctor source files for all of the specification documents. All of those source files are in open source on the GitHub repository. And they're being distributed under CC by 4, which basically means you can do anything you want to them. You can remix your own documentation. You can create an OpenCL manual with just the extensions you use and not all of the others. And you can distribute that documentation however you wish. Of course, we use that source documentation to create the canonical spec, which is on the Khronos website. That doesn't change, so you can always go back to the canonical spec. But other than that, you can remix anything you want. And also last year, if you remember, we put the conformance tests into open source as well. So you can take the conformance tests, run them on your favorite vendor's implementation, make sure everything is okay on your platform. We can accept bug fixes and merge requests into the tests as well as the specs. And as I say, we're actually getting some engagement with the community, so we're really happy to see that both on the tests and the specs. So we're fully committed to keep that level of openness as we go forward. OpenCL adoption, I'm actually interested to, over beer, understand what kind of applications here are represented this year. From our experience, I think kind of the hotspot in current OpenCL adoption is desktop apps that need portability across different platforms. There are actually more applications on this slide than there were last year, people beginning to adopt it. I count the number of GitHub repositories that are using OpenCL as another broad measure of adoption. So last year we had just over 4,000, this year almost up to 6,000. So that's a pretty good growth, a healthy selection of different languages being used in the OpenCL projects. C++ hits the top of the list. And I guess it's a sign of the times. The top repository this year is Ethereum mining, but oh well, what are you going to do? The OpenCL continues to be used as language library backend. More and more libraries, particularly in the machine learning space, now providing OpenCL backends. There are literally hundreds of libraries and frameworks that continue to use OpenCL because it is really the only way to access runtimes across many different vendors in a portable way. And as mentioned, that things were kind of the same and stable. This is the same chart as I had last year. There are no changes to this chart. No new... what this chart is, I should explain that first. What this chart is the first conformance implementation of each version of OpenCL from the different vendors. So we don't have any new vendors shipping versions of OpenCL, and the vendors haven't upgraded their OpenCL versions. So we're still 2.1 on the desktop, mobile is on 2.0, embedded on 1.2, and FPGAs at 1.0. So I would say we're stable. This doesn't quite give the whole picture though. There's actually been a bunch of submissions into the adopters program since the last IWOCL. For example, NVIDIA, we've upgraded our 1.2 for all of the current GPUs that we ship, both on Windows and Linux. Qualcomm has been submitting more, the latest GPUs on Android 8. Intel has been upgrading their submissions on Windows 10 too. So things have been refreshed and upgraded, even if we're not hitting the new versions of OpenCL as they get rolled out. And I think as we figure out what we do next, it's kind of interesting to try and understand that chart. So I think there's kind of three main lessons that the working group is extracting from this. First of all, OpenCL 1.2 remains stubbornly the baseline for OpenCL that's deployed pretty much everywhere. Why is that? And again, we would love to get your views, but some of the views I've heard, mainly drunken views, is SVM is the big headline thing in 2.0. But for the desktop GPU vendors, we kind of hate SVM because it sucks your performance, and so it's like kind of a friction point there. So I think that's partly some of the explanation. Of course, SVM is much easier on mobile and embedded devices where you have unified memory. So SVM is good, but some vendors don't see the value. And there are a bunch of other 2.0 features that are less controversial, and that's why you see this 1.2++ is actually what's shipping in the desktop right now, but not 2.0 across all of the vendors. We haven't had any new DSP vendors ship, and to me this is kind of the biggest opportunity, and it's only the high-end DSPs that are shipping conformant OpenCL. I think this is like a very straightforward reason. In hindsight, the current OpenCL specs are very desktop or HPC focused. Back in the day when they were being drafted, DSPs weren't such a interesting platform. The embedded inferencing and vision processing wasn't such a key use case. And so there are obvious things that we have done to lock out the DSP vendors that don't want to have full IEEE 32-bit floating point. That's something that we can fix. And last but not least, no 2.2 implementations shipping yet. What's going on there? Well, one view is don't panic. It's actually quite common in OpenCL land for there to be a 1 to 2 year gap between the specification being finalized and the first implementations to ship. So by that measure, we're not late yet. And there's no doubt that the SPIR-V ecosystem is evolving rapidly. There's a lot of interest in SPIR-V, and OpenCL 2.2 is largely reliant on SPIR-V ingestion, providing you the C++ kernel language. So the C++ kind of comes for free. There's open source front ends. So that's one view. It's about to hit any moment now. Or perhaps we kind of misjudged it. Perhaps there's no interest from the kernel writers in C++. They preferred us to stick with C. Perhaps the SYCL style, single source application with C++ being used in a single source file that gets compiled down automatically into kernels and host code is where the C++ interest is. Question mark, question mark. So get us drunk and talk to us about it. We'd really love to make sure we understand that. But I mentioned SPIR-V. I've said it many times, I'll say it again. I think SPIR-V is just as important as OpenCL. It's central to the whole language ecosystem. And I'm sure most people here are very familiar with SPIR-V. But in case you're not, it's the Khronos defined standard that is an intermediate representation. It's different to LLVM. It has native representation for parallelism and graphics. And it's been designed to be easy to parse, easy to transform, easy to manipulate. If you're a developer, it means you don't have to ship the source of your kernels anymore. You can select your front-end compiler and use it across multiple vendors. It should mean your drivers don't need to have a front-end compiler anymore. They're more reliable, and it reduces runtime compile time. So, and we're finding what the hope when we first started SPIR was that there would be enough vendors using SPIR that there would be a need and an opportunity for vendor-independent tools to emerge to enable optimization and manipulation of SPIR, and that indeed has occurred. And now we have significant interest and activity in SPIR-V tools, and SPIR-V is now being ingested in multiple runtimes. But it's worth remembering that SPIR originally was an OpenCL thing. It's now being used across OpenGL and Vulkan, as well as OpenCL. But we started out with SPIR-V 1.2, sorry, SPIR 1.2 and SPIR 2.0 that were based on LLVM. We learned the hard way that LLVM it's not a spec, it's an open source project, so it has a pretty dynamic roadmap. So in the end, we decided that we had to create our own stable version of a specification that we could build our own ecosystem around. So SPIR-V was the first version of SPIR that was used by both OpenCL and Vulkan, hence the V. And now it's been joined by OpenGL. The number of languages that it supports has grown. It's no longer just OpenCL C, it's OpenCL C++, GLSL and HLSL in the graphics space. And again, if you're not so familiar with SPIR-V, one thing to remember to avoid getting confused is that there are different dialects of SPIR-V. Each host API, like OpenCL, like Vulkan, defines their own environment spec, which is basically defining which parts of the totality of SPIR-V actually gets used in that host API. So those subsets will differ slightly between the APIs, but certainly the core of SPIR-V is common between all of the different APIs that ingest it. But although we moved away from LLVM for SPIR-V, we love LLVM. We're not trying to compete or damage LLVM in any way. In fact, lots of the vendors' tool chains, I'm sure lots of developers' tool chains too, actually rely both on SPIR-V and LLVM. And there's so much goodness in the LLVM ecosystem. We find it's very common for people to have SPIR-V, to take it over into LLVM, use the LLVM tools, bring it back into SPIR-V. We do find if you're using Khronos API, SPIR-V tends to be the rendezvous point where everyone ends up. But we're doing everything we can to make sure that SPIR-V and LLVM cooperate together. And in fact, since last IWOCL, we have established a new subgroup under OpenCL. We call it a TSG. So if you're talking to a working group member, your magic decoder ring, if they say TSG, it means that's a subgroup of the working group. But this is a group of people, it's been chaired by ARM, that really see an opportunity and they have a desire to be much more proactive in how we coordinate between the LLVM and SPIR-V ecosystems. So we want to outreach much more, have a place to come back and coordinate and discuss what we should do, how best we can use our resources. Some of the early projects, this subgroup's been going about a month, so it's still pretty new, but already we're looking to produce a new version of the translator between SPIR-V and LLVM, mainly focused on OpenCL environment spec, but also including Vulkan over time. It's all been done in open source, of course. And perhaps the big one is we want to have SPIR-V as a supported backend for Clang. So lots of the front-end work in the LLVM ecosystem can output directly to SPIR-V. And we have this kind of diagram, which it was David from Google that made it. It was a cool diagram, so I had to steal it. But it has an important message in that in the past, Khronos was mainly focused on the specifications and the conformance tests. Increasingly, Khronos is trying to figure out how we can be more effective at enabling cooperative tool creation. And this subgroup, I think, is a good step in that direction. So if you look at the overall SPIR-V ecosystem, this slide gets more complicated every year. This has got significantly more dense since the last IWOCL. You can see the various languages. Perhaps the really interesting one, well, SPIR-V 1.3 launched. That was increasing the Vulkan SPIR-V. So SPIR-V 1.3 goes hand in hand with Vulkan 1.1. But for the OpenCL folks here, the SPIR-V optimizations down in the blue box in the bottom left is really kind of where the action is. A lot of code optimizations, dead code elimination, and those tools continue to evolve every day. So you'd be welcome to come and help us improve them. So that's kind of where we are. So let's switch gears and say, okay, well, where would we go next? And as I mentioned at the beginning, deployment flexibility, both for implementers and developers, is kind of the key word. I think it's the way we'd sum it up. And in terms of the roadmap, we have three main initiatives. And these are similar to what we were talking about last year, but we have a little bit more clarity on what we were talking about last year. This one hasn't changed, and Michael and Andrew are going to be talking about this later. SYCL is gaining a lot of interest in the industry, and the long-term view on SYCL, I won't go into too much detail because they're going to talk about it, but the long-term view is that SYCL is our vehicle where we can take the learning experiences from OpenCL and how to generate parallel code and help bring that into ISO C++. And that's a really worthy goal. It would be great for SYCL not to exist. There's other projects out there, C++ AMP, even CUDA. They're all feeding into ISO C++ to enable developers with parallel capabilities without having to use anything but a standard language. So I think we're all bought into that vision, and a lot of expertise around SYCL hopefully is helpful to the C++ group. The other one we talked a little bit about last year, but we have a lot more clarity this year, is leveraging Vulkan to provide more deployment flexibility for people that have invested in OpenCL code. We would like to be able to enable people that have sometimes very large investments in OpenCL kernels to be able to, if an OpenCL is not available on our target platform, but Vulkan is, to be able to use the Vulkan runtime as a way to dispatch your kernels. And we'll talk more about that. And last but not least, of course, the mainstream roadmap for OpenCL. What is OpenCL next going to be? And again, the keyword, deployment flexibility across many more types of processor than we really addressed today. And we'll talk about each of these in turn. Let's start with SPIR. As I say, I'm not going to talk too much because people that know what they're talking about are going to follow me. But SPIR is kind of really cool. And a lot of applications and libraries are finding that this is a much easier way into the OpenCL ecosystem than using OpenCL directly. I'm sure many people are familiar here. It's basically use standard C++. You use lambdas and templating to guide the compiler tree to take your device code and your host code into the right compilers, and you can get pretty good performance. A lot of the libraries are finding this is a really fast and easy way to tap into OpenCL performance. And as you mentioned, Khronos is engaging fully with the ISO C++ group to try and help bring this kind of capability into C++ itself. There are multiple implementations, including Tricycle, which is an open source implementation, and more details at the link. Michael's going to be talking about the SPIR roadmap. We're working on the conformance tests and the adopters package for 1.2.1. 2.2 has been released provisionally, and 2.2 is really intended to let people get to the OpenCL 2.2 goodness through single source C++. So that's still work in progress. But looking forward, again, we want to align ourselves with the ISO C++ work. And I'm sure Michael and Andrew are going to talk a lot of interest from the machine learning vision inferencing, which is why safety critical applies to SPIR as much as the underlying OpenCL. Vulkan. So Vulkan is getting a lot of industry adoption, so we want to leverage it. So let me spend just a couple of minutes giving you an update on where Vulkan is in its adoption path. So if you remember from last year, Vulkan is a new generation GPU API, similar to DirectX 12, in that it's very low level, explicit. You get to control the GPU precisely how you want. There's no making it easier. You get to allocate the memories, you get to synchronize as computation flows through the pipe. And that's what the developers ask for, particularly in the graphics space, for getting good portable high performance from their GPU hardware. Metal from Apple is kind of explicit. It's a little bit more like OpenCL plus graphics. But these three new generation APIs, DirectX 12 is just on Windows 10, Metal is just on Apple, and Vulkan is everywhere. So it's on Windows 10 and Windows 8 and Windows 7. It's in Android, on Linux. Nintendo Switch has Vulkan, and Apple doesn't ship Vulkan natively, but we are developing some porting tools to enable people to take their Vulkan code onto Apple platforms. So I'll talk briefly about that. So we shipped Vulkan 1.0 just over 2 years ago, and it's now pretty pervasive. In the gaming space, all the engines are using it, a lot of the applications are using it. It's in the cloud, it's embedded, it's in mobile, desktop. It's in lots of interesting places. Vulkan 1.1 was launched at GDC on March 7th, and it adds all of the extensions that came into 1.0 now being integrated into core. But just like OpenCL, we're trying to not just ship a spec and forget about it, we're trying to build a much wider ecosystem. with lots of tools and widening the number of platforms that Vulkan is available on. And one thing that we've done is, so we're calling it the Vulkan Portability Initiative. We have now an open source tool layer, a shim layer, that will let us take Vulkan code and translate it at runtime into Metal. So Valve have used this already. They now have one of their key games, Dota 2, running on Metal at 50% more performance than the OpenCL on Apple. And that's going to be a production game. They're actually going to ship that to their users on Mac. That's open source library. It's called MoltenVK. It's still beta, so health warning, it's not fully production, but the aim is to have it running all of the relevant conformance tests over the next year or so. The Vulkan SDK has been ported onto Mac, and we're using SPIR v Cross, which is one of the SPIR open source tools that lets us go from SPIR v into Metal shading language in Mac. That first shipment is just the first platform we want to extend to. We have plans to bring Vulkan over DX12 and OpenCL. Other console platforms might benefit from this. And I mention this because a lot of the things that we're going to be talking about in OpenCL next, the ideas come from you want to take a subset of Vulkan and run it on these various platforms. How do you manage those subsets in a clean way? You want the conformance tests and the query layers and the tooling all to understand that just part of your API is available on a particular platform. And there's been quite a lot of work in the portability initiative to figure out how you would drive that from a JSON schema and have all the bits of the ecosystem working together. And some of those ideas we want to take into OpenCL next. So another really interesting project, which is new since last IWOCL, has the catchy name, CLSPV. It stands for OpenCL to SPIR v compiler. And this was originated as a collaboration between Google and Adobe and CodePlay. And it's a compiler to take OpenCL C source and convert it to the Vulkan version of SPIR v. And Adobe have successfully taken their 200,000 lines of OpenCL C kernels and deployed them and run them through a Vulkan runtime. So this is a proof of concept, and again, health warning, this is just beta. This isn't a production compiler yet, but I think it does show an interesting path forward for those people that want to deploy their OpenCL kernels on a Vulkan runtime. This is definitely an interesting proof of concept. And we're looking to make CLSPV a tool that the industry can use. It's an open source. Contributions are welcome. And we're, again, looking for feedback here at IWOCL. Can we, should we, also solve the API portability part of the problem by creating, just like we have done with Vulkan on Mac, should we produce a shim to have OpenCL being mapped to the underlying Vulkan calls, so you could actually take a full application and make it portable. Again, we'd love your input. But at the moment, we just have the compiler for the kernels. And the feedback from Adobe is that that's by far the bulk of the work. Rewriting 200,000 lines of kernels is not something that they want to do. And now they can just use them in, they want to use it on Android. That's why they've initiated this project. So how are we going to refine CLSPV? So CLSPV, it's a compiler, so it's been shaped by the workloads that have been put through it. So we want more workloads to be used by the project to make sure that the compiler can cope with the kernels that people want to deploy in real applications. So the process is, the working group is trying new kernels. We're inviting developers here to participate. If you have some test kernels with some interesting use cases, we're opening up repository, so you can donate those if you wish, and those will be actually integrated into a long-term testing and regression program. If we can tweak the open source compiler to cope with those new kernels, that's great. If we find that there are real holes in the Vulkan compute model that make that mapping painful, then we can propose or we can support additions to the Vulkan compute model over time. Vulkan is already increasing its compute model capability. We have now 16-bit storage, variable pointers, and some things that you'd use for vision and image processing, like compact memory types and operations, potentially coming pretty soon. So, think about, you probably wouldn't want to contribute your production kernels, but if you can reduce your kernels down into the key operations that you would really love to be able to compile cleanly, and if deploying on Vulkan is of commercial benefit to you, then again, you're invited to participate in this process. So, last but not least, let's talk about the mainline OpenCL Next roadmap. A lot of the roadmap discussions for OpenCL Next came from this realization I mentioned earlier, that we have a bunch of processors out there, many of them in the embedded space, and because we've had this historical desktop HPC-centric background, we inadvertently completely locked them out from being OpenCL conformant. Many of these smaller processors do not have the levels of precision. They don't need it for their markets that they're trying to address. And this is just one example. There are many different functionality requirements that change as you go from processor to processor, from market opportunity to market opportunity. So deployment flexibility is the key. So for OpenCL Next, the key goals that we have, we want to enable OpenCL to be conformant on way more diverse set of processors and platforms. We want the implementers of OpenCL to be able to precisely target their markets without having to implement a bunch of stuff that's just wasted because the OpenCL spec says you have to. It's not adding any value, and basically expose precisely what's in your hardware. And the way we want to enable that is by providing a clean mechanism by which we can make functionality, some features inside OpenCL optional, so we can provide this deployment flexibility. And we're talking about making features optional in both the API and the languages. And of course that means we need an enhanced query mechanism so the applications can cleanly discover what capabilities are available on their particular platform. Now, the danger, of course, is fragmentation. So to battle the potential fragmentation, we also have stolen the idea from Vulkan of feature sets where you do actually open up the implementations to ship any features they want, but you encourage the industry to coalesce around feature sets that are designed to address the needs of specific vertical markets. So the way we kind of see this working, and this is tentative, so again, get us drunk and you can have a lot of influence. First of all, we slice and dice, and we haven't decided yet how we're going to slice and dice precisely, but we know we're going to have a bunch of features that we want to make optional. And this is current OpenCL 2.2. Now there'll be some features in there that we make optional. OpenCL Next will also have some additional features. Again, we haven't decided what they are yet, but there are some bits and pieces that we'd like to add. They would probably be optional features too. We can define a feature set, for example, which is just OpenCL 2.2. The existing profiles and devices are not going away. We're not going to make any changes that breaks existing applications. This is an additional query mechanism that gives you more definition into precisely what features are going to be available in OpenCL Next, which has this deployment flexibility. So Khronos also would define a 1.2 profile too, exact equivalent to the existing profile today. But the interesting thing is you can define any feature set you want. And an industry-defined feature set, for example, vision processing or inferencing that might well be interesting to a sufficient number of OpenCL vendors that we find the industry can coalesce around that feature set definition. They can get to decide what's appropriate for their markets and their devices, but encouraging people to come together to agree that everyone should support at least the baseline will help the developers and not throw everyone into fragmentation. So this is definitely where we need your input. We're still brainstorming the details on this. So if we have the idea of industry-defined feature sets, now who should define it? Khronos doesn't necessarily regard itself as the expert in every possible domain. So we would kind of like the industry to figure out which features should be in a particular feature set for a domain that we may know little about. But what process would we use? How would we encourage people to come to consensus? We see there are some vertical opportunities. The ones that we're already thinking about are in the embedded space that I mentioned. Perhaps this is also a mechanism that we can use to get past the 1.2 logjam. If the desktop vendors were to come together and say, okay, well, we can all agree at least there's this 1.2++ set. Let's make a feature set about that. So that would actually raise the bar on the desktop for a set of functionality that would be reliably available from all of the desktop vendors. Perhaps that would be useful. We want to provide an incentive to the OpenCL vendors to actually coalesce around these feature sets. So we're discussing how best to do that. Perhaps providing a new level of conformance. So if I have the inferencing feature set, if I'm conformant to that feature set, in other words, I have all the features I need and all those features are tested to work, I can actually use my marketing badge. I get marketing brownie points by being conformant to that feature set. That means I can sell my OpenCL implementation into the inferencing marketplace easier, better, because I have that badge of honor for the supported feature set that people are interested in. So again, should we do that? The precise mechanisms are being discussed right now. Please let us know your thoughts. I mentioned safety critical. It's closely related to the embedded space. It's coming at us really fast. It's going to be key for lots of different markets. Khronos already has some experience in safety critical. We have OpenCL SC, which is originally for avionics cockpit displays, now automotive displays. But we're entering the era of autonomous machines where safety critical is going to be needed everywhere. The OpenVX, which is the vision processing library from Khronos, already has a safety critical version. They took some very pragmatic cuts at making it much easier to safety certify. A full OpenVX has a full graph compiler, which you define the DAG of your vision operations. The safety critical version just takes in a precompiled DAG. It means the amount of code you need to safety certify is like 20% of what it was before. And it's simple things, but really powerful things. And trying to mathematically prove that things are correct, that's really tough. And we don't need to go there. There's way more easier things that we can do in the meantime. But as it's general, we've discovered there's a general lack of understanding and consensus on what we should do for an API design to let a system go easier through safety conformance and safety certification. So we've opened up the Khronos Safety Critical Advisory Forum. This is open not just to Khronos members, but to anyone who's interested in the safety critical domain. We're trying to create a forum where the industry can come together and actually figure out how we should be designing these APIs. And those guidelines can be used inside Khronos and throughout the industry. If you're into safety critical, I urge you to consider joining the forum. There's no cost, there's no minimum work commitment, but I think it's going to be an interesting forum. We're already reaching out to other organizations and we have the ongoing work within the Khronos working groups too. And my last slide is another opportunity for you guys to get involved if you wish, if you're not already Khronos members, to let you know about Khronos advisory panels. This is where we, if you're interested, we get you to sign the NDA and the IP framework so you can participate in the design process. You don't get a seat at the working group, which kind of meets every week. It may be a blessing or a curse. But the working group can definitely share draft specifications with you, get your feedback, get your requirements, get your thoughts on the roadmap that we've been discussing here today. It's by invitation, but if you're interested, please approach any of the working group members. We'd love to talk to you and bring you on board. And we have one advisory panel right now that covers both OpenCL and SPIR. And I haven't talked to Simon yet, but we're suggesting that we hold an advisory panel session at the next IWOCL. That perhaps we can fit that in, because lots of the people we think that will be interested will probably be at IWOCL 2019, so something we might think about. So that's the end of my talk. I think, as always, the call to action is to get involved. We really want to know what you think about the proposed direction for next, how we should implement it if you think it's a good idea, the feature sets and how we manage those in particular, and there's multiple ways you can get involved. The best way is to join and have a full voice and vote, but there's the advisory panel, there's the Safety Critical Advisory Forum, or just buy a SPIR. Thanks a lot. Yeah, I think, obviously we manage the repositories for extensions to the existing specs now. And those are not just Khronos created specs, OpenCL, OpenCL Vulkan, they're vendor extensions that Khronos has nothing to do with, but we do manage the registries. So even if we do find a way of successfully enabling industries and to do what they want, I think that probably will end up being a service that Khronos can provide, in providing a single place, a repository, a registry that we can manage and make sure is consistently maintained. Yeah.
You haven't talked, well, I saw a talk by Mozilla recently, and they talked a lot about, let's say Vulkan in the browser and Web 3.0.
Yeah.
And I can't really see OpenCL having any kind of impact on that. So why would I for me, I don't look at OpenCL anymore, I'm just interested in Vulkan. And I wonder, without legacy code, we talk about why would people be interested in OpenCL?
In the browser?
Well, generally I think the browser is just an observation that OpenCL is going to struggle with the future on the bench. Well, for the seems to me motivation to look at OpenCL over Vulkan.
I disagree.
Well, that's my motion.
Yeah, because in the browser, you started with Mozilla, so the next generation WebGL is there's a lot of debate going on right now. So at the moment, the browser vendors are on the path to create a fourth native API without any input from the GPU vendors. Not enough said on that. We'll see how that pans out. But whatever happens, whether it's an API like Vulkan or Vulkan directly or a subset of Vulkan like we're doing in the portability subset, there's no doubt that it's going to be Vulkan and DX12 and Metal for the underlying APIs, but there's going to be some Vulkan-like API that gets exposed to the web developers when they're ready to go past WebGL 2. So if you want to take your OpenCL investment into the browser, the Vulkan portability path is going to be what you're going to need in some shape or form, depending on how the browsers end up. But Vulkan and CUDA, they are only for GPUs, and they have a particular model. I think it goes back to my very first comment. If we didn't have OpenCL with additional flexibility and the capability to cope with different processor types, we would have to invent it, because to say that every processor in the world is going to be a GPU is not correct, obviously. And there's a huge amount of investment in OpenCL, and people want to use it. So
maybe time for just one more quick question, and then we'll listen more. I was very interested in when you say the embedded side,
yeah.
particularly things like Android.
Yeah.
OpenCL will quite be adopted as fast. So with OpenCL, they're essentially the same problem, where OpenCL is set sheet desktops, and they had to come, and you came up with OpenCL ES,
right,
specifically for embedded devices, and that's worked really well.
Right.
And it's a single standard rather than fragmented.
Yes.
Section 3.2, not
5.6, right.
Is there a reason why we don't just have OpenCL ES?
Well, good question. I think Vulkan learned, exactly as you said, Vulkan learned from the ES schism. Because with the best of intents, if once you have two specifications, even if you're working hard to keep them consistent, they inevitably diverge in small and annoying and sometimes important ways. So Vulkan took the right path in saying, okay, we're going to have a single consistent framework, and then we're going to be able to take out features and feature sets from it to suit the different markets and the different platforms that we want to address. And the OpenCL Next direction is doing precisely that. If we created OpenCL Embedded or OpenCL DSP or whatever it would be, we would have the same schism problem. Much better to maintain a single overall specification with all of the functionality that all the different markets need in a consistent single specification, and then have this optionality mechanism to define which parts of that consistent framework you want to deploy on different systems. So credit to Vulkan for kind of breaking through their schism and coming out into the light, and I think I think it makes sense for us to adopt that same approach.